So we finished last time with sort of a start of something. Bipartite graphs are graphs which you can split into two parts, and hence bipartite, two parts, such that there's no edge internally in either side. All edges go between the two sides. Okay, so that's what a bipartite graph is, and there's a claim. G is bipartite if and only if the eigenvalues of A are symmetric around 0. And we did a hand-waving proof, and I'll do the hand-waving proof in a slightly different way. So last time the hand-waving proof was like, aha, dimension arguments. And well, okay, there's a simpler way to phrase that hand-waving proof, which is we can do a similarity type argument. And I'm only going to go one direction for right now. So, of course, when you have an if and only if, you double your work usually, because you have to do two directions, unless you're really lucky and everything's exactly reversible. All right, so what I'm going to argue is if we're bipartite, then we have symmetry around 0. So I'm going to go in that direction. All right, so how can we begin? Well, the first thing to note is that our matrix, and I know I shouldn't use A for adjacency because I also have A as subset of vertices. Well, okay, all right. But the moral here is our adjacency matrix can be written in the following way. Namely, you split it up into two parts, and you have subset A, subset B, subset A, subset B, and it looks like, well, zeros in the diagonal blocks, and then you have some matrix in the off-diagonal blocks. And this should be M transposed. Yeah, we're keeping it symmetric. All right. Now, what we'll do is we'll look at the following. So we're going to take this matrix here, and we're going to do the following. So namely, I'll just copy it, and I'm going to post-multiply by something that looks like the identity in the upper left and minus identity in the lower right. But on the other hand, I'm going to pre-multiply by something that looks like identity in the upper left and minus identity in the lower right. Okay. All right. Good. Now, what have we done? In using the language of linear algebra, what's going on? And
just on the left, you turned the bottom left of the matrix into negative itself.
Okay, so what will happen here is because of the minus identity, and it always takes me a few minutes to figure out what's happening. So I'm going to sketch something here. And, all right. So I'll start with this matrix, but I'm going to use some color coding, which is to say one of these matrices will affect the rows. And so the minus signs will come through on the rows. And the other one is going to affect the columns. Columns. And so what's going to happen is you're going to change some signs. Now, which one does which? You play around with it. You do a small example, and then you figure it out. It's not very surprising. And so what you really have is because you've changed all the signs down here and all the signs in there, well, changing the sign at 0 doesn't do a whole lot. What you have is minus what you started with. Okay, great. So that's minus our matrix A. Well, that's maybe helpful if we understand what we're really doing up here.
You're multiplying by a matrix and its inverse.
Aha! Notice that this matrix looks like that matrix, but it turns out, as someone has wisely observed, these are inverses. But what does that give us? Yeah, similarity. And so the punchline is that we now have the following conclusion. So A is similar to minus A. Well, what do we know about similar matrices? They have to have the same eigenvalues. And so the spectrum of A is the same as the spectrum of minus A, which basically just takes your spectrum and flips it around 0. And so now we've established that if we're bipartite, the eigenvalues are symmetric around 0. This is really the argument we talked about last time, if you think about what was going on, because we talked about changing the signs for the eigenvectors. And so that's what this similarity transformation is doing, is changing the signs on one side for the eigenvectors. So remember, similarity matrices are really change of basis operations. All right. Well, cool. Nice. Well, we'd like to have it both ways. And so we want to argue that, oh, hey, if our eigenvalues are symmetric, the graph is bipartite. So my plan is to do a proof that we can be totally convinced of, and I'll mention a result that we may or may not be familiar with, depending upon how far down the rabbit hole you've gone in linear algebra. So I guess you could say it's sort of a sledgehammer type thing. We'll pull out a powerful tool and say, by this powerful tool, which we will not prove because that would be a whole course in and of itself. And but we don't have to. Other people proved it. That's a nice thing about math. All right. So now we're ready to talk about what can we use the adjacency matrix for, and the big aha. And if you've ever had anything in spectral graph theory, you almost certainly know this result. So the adjacency matrix is really good for counting walks. So you can think of it as the walk counting matrix. And it's built around counting walks. And what do I mean by that? Well, here's a result. And so we'll state it. Maybe we'll call it a theorem, just so that it sounds important. Theorem. So if you take A to the power k, and you look at the entry u comma v. So remember, we think of our matrix as being indexed by the vertices. So I'm looking at this says u is a vertex, v is a vertex, and so that makes sense. And I'm raising a to a power, well, that means I'm doing something to it. It's a square matrix, so I can still talk about the indexing. And the claim, the theorem, it says that this is the number of walks with k steps starting at u and ending at v. All right, so that's the theorem. Okay, well, we should try to convince ourselves. Okay, let's try the case k equals 1. So if I take a to the power 1, what do we get? You get a, right? Now what is a? Well, you might recall a is 1 if u is adjacent to v and 0 else. Well, okay, but now let's think about it in terms of walks. How many ways are there to take a walk of length 1? Well, there's either 0 or 1. 1 if you're connected, and 0 if you're not. Okay, so it's true for A. So we proved the base case. Well, actually, we haven't proven the real base case. K equals 0. All right, A to the 0, what is that? It's the identity. Yeah, so how can you take a walk of length 0 between vertices? Well, the only way you can take a walk of length 0 is to not move. And so there's exactly one of them if u equals v, and 0 if you're not, which is the identity matrix. Okay, cool. So we've now proven 2 base cases. And so, it must be true if you've proven it 2 cases. I mean, if we were physicists, we'd already have moved on. But all right. So cool. Well, let's do an argument, and it's an induction argument. So induction, proof by induction. So how does it go? Well, no surprising. We assume it's true for k. Okay. And we've done some base cases. So the base cases are done. And so we're not going to recheck those. And so we're going to look at a to the power k plus 1 of uv, that uv entry. All right. Well, what can we do? And don't worry, it's not like I'm going to fit the whole thing here. If you're like, my gosh, how are we going to fit all that in this space? We're not. We're going to go on to another page. But we'll start it here. Now, it turns out, true story, a to the power k plus 1 is a to the k times a. I know. It's good stuff. All right, now at this point, we just have to remind ourselves about matrix multiplication, and in particular, what does it mean to look at the UV entry? So what's going to happen here is we have our matrix A to the K, and we have our matrix A. And we're looking at the UV entry. Well, that says you do the following. We're going to come to the uth row of A to the K, the vth column of A, and we're going to do what you could call it dot product. So that's how we do matrix multiplication. Is that, everyone feel good with that? All right. So let's see if we can remember how to write that down. Okay, so here we go. We're doing our A to the K plus 1, U comma V. So we're going to take the sum, and well, this is when we run into trouble with subscripts. So the sum over W. So W is just moving ourselves down. And we're going to take our A to the K, U comma W, and then we're going to multiply A times W comma V. Okay, so this is what happens when we do this step. All right, well, now we apply our induction hypothesis. So this is the sum over W. This is the number of walks of length K from U to W. That's just the definition of what A to the K, U comma W is. Nope, that wasn't me, that was the projector. All right. And then A of W comma V, well, this is going to be 1 if we have an adjacency and 0 else. All right. So we're doing that multiplication. So, all right, being a little bit loose in our terms here, but that's okay. All right, now what happens? Well, the key here is to just think about what's going on in your graph. So here's our graph. And we're starting at U. We want to end at V. And we want to get a walk of length K plus 1. Well, what has to happen is every walk of length K plus 1 is going to come up and just be slightly short and then take one more step. And so we say, okay, so what we can do is if I want to count the walks of length K plus 1, I really go to all the individual neighbors and I say, well, how many walks are there of length K to those neighbors? And I add those all up. And then each walk gets represented. Each walk is accounted for once and only once. So in terms of our picture, if we now think about what's going on here, well, I only have to keep the W, which is adjacent to V. So this is really the sum of W adjacent to V of the number of walks of length K from U to W And we say, aha, the picture tells us, well, that's how we form all possible walks of length k plus 1. So this then becomes the number of walks of length k plus 1. All right. So that's one way to argue it, if you like to argue it by induction.
To V.
U to V, yes, thank you. And you can argue it more directly if you're willing to sort of bite the bullet and say, well, what does it mean here? So if you take matrix multiplication, so suppose I look at AK U comma V, the way we talked about multiplying two matrices together, but you can actually multiply any number of matrices together. It just, you have to be willing to bite the bullet, so to speak, when it comes to notation, because it gets a little bit messy. All right, so this becomes the sum, and we'll have, W1, W2, up to W sub k minus 1. Yes, we need k minus 1 intermediate terms. And this becomes A U W1 times A W1 comma W2 times ... all the way up to A. And then it'll be W k minus 2 W k minus 1, and then A W k minus 1 V. So that's matrix multiplication, which is like, okay. But now, if you are willing to accept this, and it's not hard to believe this, what do we see? Well, each one of these terms, what can we say about those values?
One is adjacent to the others.
Yeah, you get a 1 or a 0 from each individual piece, because it's either adjacent or it's not adjacent. So the only way you can get a 1 from the product is when we have what? Is if we have a walk. Everything's adjacent. So 1 from the product only for the walks. And each possible walk is being tested here. And so the punchline says, okay, you get a 1 for each walk. Each walk has been checked, so this becomes the number of walks. So you can do it this way as well, if you prefer not to, say, use induction. But you can do this. All right, great. Whew. All right. So now you know spectral graph theory, because usually when people say spectral graph theory, this is like, oh yeah, you can count walks. And it turns out counting walks is a really cool thing to do. And so some of the things that I've done in my research, which maybe isn't spectral graph theory per se, but when I try to do enumeration problems, oftentimes I think about, well, can I think about how I can build things sequentially? And so I can describe counting by walk taking. And then I say, okay, great. Now all I have to do is raise a matrix to a power and read off the right entry. So many years ago, there was a project that was started, did it with 2 grad students, saying, well, let's count the number of ways to cover a Tetris board using Tetris pieces. So, tetronymos. And we reduced it down to saying, well, we just have a walk. So all we have to do is take a particular matrix and raise it to, it turned out, the 20th power, and read off an entry. Now, the only small caveat was that the matrix had roughly size 10 million by 10 million, but beyond that tiny detail, the idea is simple. And well, there's ways to get around that as well, but that's a different story. All right, so we now know that we can count walks. So let's do some applications. And let's talk about the traces. Well, the trace of a matrix, do we know what that is? Or do we remember what that is? Trace of the matrix is sum of diagonals. Now for us, we're talking about counting walks. So what is that going to be translated into? when I look at the diagonal entries?
Of just A or of A to the K?
Well, either one. But generally A to the K includes just A.
Sure. It'll be the number of K-length walks from the itself.
Right. Is there a nice term for that? Ooh, not cycles. We got to be careful.
Oh, because they're walks.
Because they're walk. Well, we call them like closed walks. Yeah, yeah. The thing you have to be careful about is like, you know, it's one of those things that where in graph theory, we have all these terms, and you have to be like, well, cycles imply something, and you know. So yeah. So for us, we say, okay, so now we want to count closed walks. Cool. Cool, 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 cool. All right, so here we go. What can you say about the trace of A? Okay. Sure. Yeah. No, there's no closed walks of length 0. Good. Now, what's another way to compute trace of A? Sum of the eigenvalues. So the sum of the eigenvalues of the adjacency matrix must be 0. Okay. How about trace of A squared? Well, think of closed walks of length 2. So I have to take 2 steps. I have to be back to where I started.
It'll be the number of... No. Oh.
Isn't it 2 times the degrees?
Okay, so some people mention sum of degrees. Yeah, because if you look at A squared and just look at the diagonal entry, what will happen is you'll get back from a neighbor and back to itself. So the diagonal entries are the degrees, and so you could say it's the sum of the degrees. So sum of the degrees, but we have a result about the sum of the degrees. Theorem 0. Do you remember that one? 2 times the number of edges. All right. Well, what's another way to compute trace of A squared?
It's the sum of the eigenvalues of A squared.
Yeah,
Sum of the squares of A.
some of the eigenvalues. So now, if I know the eigenvalues, I can compute the number of edges. So the eigenvalues tell me how many edges my graph has. All right. Well, how about trace of A cubed? Well, okay, so when we talked about here, number of edges, so why was it twice the number of edges? Because for an edge, you can just go back and forth, right? So where did the 2 come from?
Because you can start at either versa.
Right, because you could have started at U or you could have started at V. So there's really, for each edge, there's 2 walks of length 2. All right, now trace of A cubed, you have to take 3 steps, and we're going to keep things simple. All right, so what can we do? All right, so we can do a triangle. U, V, W. All right. Is there anything not triangle that can have a walk of length 3 and get back to itself? No. Yeah, we're keeping it simple. Okay, so how many times am I going to count a triangle?
I want it to be 3, but I'm afraid it's 6.
Why are you afraid it's 6? Are you like, oh no, 6, ah!
Yeah, exactly.
So you can choose an initial starting place, and then you can choose a direction. All right, so you get 6 times, oops, not number, 6 times number of triangles. And all right, so that's the cubes. All right, cool. Now, let's try maybe trace of a to the fourth. No, it's definitely going to be a lot different.
Yeah.
Yeah.
So how many ways can you take 4 steps and get back to where you started?
Okay, so it's going to include.
All right. I'm seeing some wonderful hand gestures where it's like,
Yeah.
okay, so for each edge you can hop back and forth 4 times.
But you can subtract the frequency, so you get the rest of it.
All right, so we have 2 times the number of edges, right? Because we can pick a start. All right, what else do we have?
A cycle of length 4.
Okay, so we can do a cycle of length 4. And this is a proper cycle of length 4, all distinct vertices. How many of those do we have? Or how many times will each cycle get counted? 8. Okay, plus 8, I'll just put C4. So 8 times how many copies of C4 you have. All right. Anything else? I see it.
Couldn't you go to some neighbor back to another neighbor back?
Yes, you could have
Walks of length 2 and
something that looks like that. All right. How many of those are there?
every neighbor has.
Now, I'm not claiming you can compute this easily in terms of eigenvalues. Just sort of think, how could I compute these things? If you like, think about the following question. How could you compute how many P3s your graph has?
It would be like the sum of a row in A squared. The sum of,
Well, sure, okay.
because it's the number of length 2 walks.
I agree, it's number of length 2 walks. Yeah, so some of the degrees choose 2. Because what you do is at each individual vertex, you pick 2 neighbors. So essentially, you count based on the middle vertex. So for each vertex, you say, okay, what if you were to the middle? How many ways could I find the 2 ends? All right, so we have the sum over all V in the vertices, the degree of V choose 2, and what goes in front? So
4? No. 8.
I liked 4 because
And you can choose which vertex.
But you also have choice which vertex you get. So you have a choice which vertex you go to first.
well, it depends where your start is, right? Because you could start on an end, and if you start on an end, you have to go middle, other end,
If you're
back
in
to
the
middle,
middle,
back to
you have
end.
2 choices, and the others have just 1 choice.
But if you're in the middle,
No, you're right. I'm sorry. I got confused by the fact that those arrows, there are 2 arrows, and for some reason I thought
Oh,
there
sure.
were 2 edges between each pair.
okay, so you are right.
That's not how it
That's an easy thing to confuse with, but yes, it should be 4.
Yeah, I agree.
And of course, you may have already noticed it's getting more complicated, which is why we're not going to write down the next expression. But if you were going to write down the trace of a to the 5th, and perhaps there might be a reason you'd like to explore this, what would you want to look at?
You would want pause.
Pause. Good.
Yeah, a C5.
C5s.
Triangles.
Oh, yeah, triangles with an extra thing on it.
Yep. Triangles where
One of your triangles. Anti-pause.
so that's the kind of thing that you get to look at. And of course, in general, it keeps getting more and more complicated. Okay, so let's make a quick observation here. I bled through a lot. We'll turn the page over. That will not necessarily help a lot, but that's okay. So, all right, observation. All right, if G is bipartite, What can you tell us about trace of a to an odd power? All right, we have a suggestion, 0. Why?
It takes an even number of steps to get back to yourself.
Right, because we're close, right? Because you have to jump back and forth between the two sides. And so, after an even number of steps, you'll be on the same side. After an odd number of steps, you'll be on the other side. So you cannot get back to yourself in an odd number of steps. All right, now I claim that this is enough to give us what we want. So you might say, well, what was that? So, namely, the reverse direction of what we were trying to prove at the start, which is, as a reminder, if the eigenvalues of A are symmetric, then G is bipartite. Now, this isn't quite going to give us what we want, but bear with me, you'll see that this is the right idea. Okay, so first thing to note. So if the eigenvalues of A are symmetric, okay, then what must be true about the trace of A to the 2k plus 1? Well, before you answer, as a reminder, that's the sum of lambda I to the 2k plus 1. Because of symmetry, what do we have? Yeah, so you can pair up your eigenvalues. For every positive one, there's a negative one. And when you raise it to the power 2k plus 1, they're the same size, but opposite sign, so everything cancels. All right, so the trace of A to the power 2k plus 1 is 0. All right, conclusion from this. So, if the eigenvalues of A are symmetric, and, sorry, I don't know why I'm writing every single word, then there are no closed walks of odd length.
Which is exactly bipartite graphs.
Which is exactly bipartite graphs. It's a characterization. You can, if you're a little bit like, wait a second, I thought bipartite graphs were no closed odd cycles, or no odd cycles. But it turns out a cycle is a walk, and a closed walk. And so if you had any odd cycle, you'd have some odd closed walk. But here we don't. And so this is equivalent to bipartite. So that's not a trivial, I don't want to trivialize this argument. But hopefully if you've had a little bit of graph theory before, this is something you've seen. If you haven't, the basic idea says, well look, suppose there are no closed walks, you just start by picking a single vertex and say, I declare I'm on side A. And now, every other vertex you say, okay, how far does it take for me to walk to that other vertex? Things that are even length get side A, things that are odd length get side B, and then because there's no odd walks, everything is consistent. So the labeling A and B is consistent. All right. So there we go. We've now shown that, what have we shown? Well, we've shown that the eigenvalues can detect, it can detect whether or not you're bipartite. It can detect how many edges you have. And it can also tell you something about odd girth. And I don't know if this is a phrase you've run into before. Are you familiar with this? Yes. It's a little bit of an odd phrase. If you just said, are you familiar with the phrase girth? What's the girth?
The size of the smallest cycle.
Right, the size of the smallest cycle in your graph. So what's the odd girth?
When that cycle has odd length.
Well, it's the size of the smallest odd cycle. So odd girth, this is the size of the smallest odd cycle. So you might have, even cycles, but we ignore those. But the nice thing is we can use the eigenvalues to detect the odd girth, the size of the smallest odd cycle. How do you do that? No.
Find the smallest number, the smallest odd number, which, like k, for which the sum of the eigenvalues for the kth power is non-zero.
That's right. You just keep looking at the odd powers. Now you ask, can you not detect? And I'll give you a quick example. And I think we may have talked about this, but these two graphs have the same eigenvalues. This one, the odd girth the even girth is 4 because it has a 4 cycle. This one doesn't have any cycles. And so the problem with the even powers is that ability to sort of jump back and forth across an edge. And that's why you can be misled. But with the odd powers,
It counts walks.
yes, because we're counting walks. But for odd powers, if there is an odd closed walk, then there's an odd closed cycle. There's the smallest odd closed cycle. So there's the first time you actually hit something. So that's why we can't detect even, at least not without more assumptions. All right, so let's see. How much time do we have left? Okay, yes, good. We now have enough time to sort of say, all right, so this was a way to argue bipartite implies symmetry, and if and only if. So let's bring in the sledgehammer. Perron-Frobenius. All right. Has anybody encountered Perron-Frobenius before? Oh, okay. All right. So great. This will just be a gentle walk down memory lane. And, well, all right. So there's a couple of concepts. So we're going to assume we're dealing with a matrix M. And there's 3 assumptions. The first assumption is the entries are non-negative. In particular, everything's real. Could be 0, are positive numbers. There's no negative numbers allowed. Okay, that's our first assumption. Okay, so that one, we don't have to explain what we mean by non-negative entries. Assumption 2, all right, irreducible. This one we need to explain. So say a matrix M is irreducible, basically says there's no way, no permutation that does the following. And okay, so where these are square blocks on the diagonal, a 0 in the lower left, and I don't care what else there is. So I don't want this to be a square block on the diagonals, and I want there to be a 0 down here. Okay. In the language of directed graphs, this would be called, okay, let's not use the language of directed graphs. In the language of graphs, if we were symmetric, what would we have? We'd have 0, 0, something, something. What would that correspond to? Yeah, multiple components. So irreducible, when you see that for our class, you should just say, oh, Steve's just trying to tell us connected. In the language of directed graphs, because I'm not making any assumption here about, oh, I should have said M is square. But I'm not making any assumption here about symmetry. So Perron-Frobenius does not need symmetry. All right. So we have connected. So that's one assumption. One more assumption, which is aperiodic. Okay. This one is even more confusing than irreducible. again, okay. How much hand waving am I allowed to do?
2 hands worth.
Okay, 2 hands worth. All right, good. 2 hands worth. All right. All right. So here's my 2 hands worth. So aperiodic, and I'll explain this in terms of directed graphs. So imagine you took M and you made a graph. And the way that you would make a graph with your matrix M is every row and every column is a vertex. 0 entries, don't put an arrow. Non-zero entries, put an arrow. So I'll define what aperiodic is by defining what periodic is. So aperiodic is we don't want it to be periodic. So periodic says that you can split it into more than one piece where the arrows flow in sort of one direction. The pieces don't have to be the same size. But if you have, say, 3 blocks, all the arrows go either from 1 to 2, from 2 to 3, or from 3 to 1. And so if you think about your walks, well, they're going to be repeating sort of every 3 times which component you're in. So, at things congruent to 0, you're in 1, and things congruent to 2, so forth and so on. So that's periodic. So aperiodic, the technical way you do this is you say you look at all the possible cycles that you have in your directed graph, and you take the GCD. And if it's 1, then it's aperiodic. And if it's not 1, it's periodic. So if this is a case where it'd be 3. All right, so in terms of graphs, what does aperiodic mean? So if this helps, just think of periodic as somehow being like how long it takes to get back to where you started. Or if you or maybe another way to say is think of all the GCDs of your cycles, of cycle lengths. Well, if you have an edge, again, let's think about graphs. We're keeping it simple. If you have an edge, what's the GCD well, what's the length of that cycle? If you just use that edge, go back and forth. 2. So the greatest common divisor is either 1 or 2. Because as soon as you have an edge, you have a cycle of length 2. All right. So when is my greatest common divisor going to be 1? And when is my greatest common divisor going to be 2?
When it's non-bipartite?
It's 1 when it's non-bipartite. Why is that?
It's 2 when it's bipartite?
Because it's 2 when it's bipartite. Very good. When it's non-bipartite, there's an odd cycle. GCD of 2 and an odd number is 1. Okay, so aperiodic means non-bipartite. Now, we'll make a little note here. Bipartite has GCD of cycle lengths equal 2. And this will come into play in just a second. All right, so these are our basic assumptions. What's the conclusion? So let's assume that we are indeed, entries are non-negative, we're irreducible, and we're aperiodic. The conclusion, which we've run out of space here. All right, so, all right, irreducible plus aperiodic. The conclusion is that if you look at your eigenvalues, there's one eigenvalue here of maximum size. And it's real. Every other eigenvalue is smaller than that. So the remaining eigenvalues are strictly smaller. All right, that's good to know. And there's one other nice fact which is not only do we have this eigenvalue of maximum size, it has a really nice property for its eigenvector. I know a few people said they've seen Perron-Frobenius before. What do we know about the eigenvector of this eigenvalue?
And have it have all non-negative entries.
Oh, you can be even more positive than that.
Have positive entries.
Yeah, has all positive entries. So you can actually know whether or not you found the largest eigenvalue, an eigenvector. If you have an eigenvector with all positive entries, that is the eigenvector for the largest eigenvalue. All right. Now I said this was a hammer that you could use to prove bipartite. So here is...
Why can't you have multiple eigenvectors for all positive?
Yeah.
Try it. Well, because they wouldn't be perpendicular.
Oh, you can't make them orthogonal.
Yeah.
I see.
And
If it's
so,
all positive, then you're required by orthogonality.
yeah. If one's, yeah.
That's sneaky.
So, all right. If you're irreducible and periodic, so here's what happens. All right. Someone give me a, what's the periodicity?
3.
3. Okay, so what you're going to do is you're going to, you'll have n eigenvector, eigenvalue again here, and it's not going to be the unique largest. And, whoops, sorry about that. And what you do is you split up by cutting it into 3 equal chunks. And so you're going to have eigenvectors at those points as well. And here's the fun thing, is if you look here at this part, whatever eigenvalues you have there will translate over, so by a rotation. And they will also translate over by a rotation. So the eigenvalues are symmetric by rotation, depending on periodicity. Okay, so how does this give us bipartite? Well, when we're bipartite, we're periodic. What's our periodicity? 2. What does that translate into in terms of picture? Well, what it translates into is just a 180-degree rotation. But because we also know our eigenvalues are real, what's going to happen is that all the eigenvalues here on the positive are just going to flip over by rotation and become exactly symmetric, about 0.